smaller than this because A4 is smaller than A3. And this smaller than this because these things are smaller than A5 through A7. And once again, and you go out to the last term, whatever AN is, right? And this goes out to TK. But the point is, if, yeah, and this isn't dot, 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 but this goes out to TK and AN. Nice. Okay. N is bigger than 2K. If N is bigger than 2K, then what we have a good comparison. We have TK is less than 2SN. And then we'll use comparison here. And if the SN converges, so does 2SN. Okay? So that's the idea. Very nice, beautiful idea. All right, so great. It might just be a curious theorem, except that it's actually extremely useful now to show what happens to sum of reciprocal powers. Yes? Yeah, well, remember, we are talking about infinite series in the theorem. But infinite series are really sequences of partial sums. Those are finite. That's right. And so we're back to working with the finite, which is what we want. But we now have to just figure out what that limit is. OK, so here's the application. Let's come back to 1 over n to the p. Check this out. I claim this sum, 1 over n to the p, converges just as you claimed if p is bigger than 1. And it diverges if p is less than or equal to 1. Let's prove it. Can you see what we're going to do? This is so cool. This is just so cool. OK, let's first dispose of a case where it's clear it doesn't converge. If I take p less than 0, then this just becomes powers of, it's 1 over n to the minus 2, right? That's n squared, sum of n squared. Clearly doesn't converge. Terms don't go to 0, yes? So as long as p is less than or equal to 0, the terms don't go to 0. They don't go to 0, so it diverges. So the series diverges. Get that out of the way very quickly. So if p is bigger than 0, then, OK, there might be positive somehow here. Check this out. We're going to use the previous theorem. We'll take a look at the series where you pick out the 2 to the kth term. So there's 2 to the k. And what's the 2 to the kth term of 1 over n to the p? That's 1 over 2 to the what? Kp. That's what I'm looking at now by the previous theorem. But what is that? This is 2 to the 1 minus pk. It's the sum of 2 to the 1 minus pk. What kind of series is that? Where this is a sum over k. It's geometric. Beautiful. And we know the geometric series converges when the ratio is strictly less than 1, 2 to the 1 over p, right? Which converges exactly when, if and only if, 2 to the 1 minus p is strictly less than 1. But when is 2 to the 1 minus p strictly less than 1? So this is true if and only if 1 minus p is less than 0. And so that's, in fact, gives us the condition p bigger than 1 is when it converges. So this is only true. This is true if and only if p is bigger than 1. And it diverges otherwise. Okay, so we've just answered our question, sum of the reciprocal powers. very nifty. Took a little work, but now actually we have a very good set of things to compare to. We no longer have to just rely on geometric series or harmonic series. We have all those series, the reciprocal powers we can use now as things we know convergence or divergence of. Okay. All right, great. Now let's finish with a cool application. Here's a series that arises in many contexts. 1 over n factorial, Taylor series being a prime example. Anybody know what the sum of the reciprocals of the factorials are? Sum 2? This sum actually goes from 0 to infinity. 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial. Anybody know what it converges to? First of all, does it converge? That's a question. How many people say it converges? Yes, you're right, it converges. Good. Okay. And it converges to a limit we call E. To something we call E. That's how we can define E this way. Okay? But let's just convince ourselves it converges to something. Well, why does it converge to something? Help? Use any of the theorems we've talked about before. Partial sums are, okay, yeah, the terms go to 0 doesn't necessarily mean it converges, right? If the terms don't go to 0, we know it diverges, but if it goes to 0, well, it may or may not converge. What else do you know? Are the terms non-negative? Yes, good. So terms are non-negative, so this sequence is increasing. So if we could show it's bounded, we're in good shape. The partial sums are bounded. Are they? Yes! Its partial sums are bounded, and that's easy to show. Look, would you agree the partial sums are bounded by this is less than 1, this is less than 1, this term is less than a half, and would you agree with the next term, 1 over 3 factorial, is less than 1 over 2 squared? Because this is 1 over 2 times 3, and this is 1 over 2 times 2. Yes? This is smaller. Would you agree the next term is actually less than 1/8? Because this is 2 times 2 times 2, and this is 2 times 2, 3 times 4. Yes? So if you add up these things, its partial sums are bounded. In fact, they're bounded by what? If you sum up this, the most it can be is what? 3. This is the idea, right? Good. Partial sums are bounded. It's non-negative. And the terms are non-negative. Nice. So it converges to something. Let's call that number E. We'll call it E. We don't know anything about E. Well, I do. But let's call it E. Here's a question for you. How fast does this converge? I claim this convergence is actually very rapid. The convergence is rapid. Why? Check this out. If I take E and I subtract off its nth partial sum, so the partial sum here is, I didn't write it out, but let's call the partial sum S. This would be S sub 2, and this would be S sub 3. Go out to the nth term. What do you get? Well, that's just 1 over the sum of the reciprocals from n plus 1, right? Okay. But check this out. Would you agree, whatever this is, I could factor this. I can factor out a 1 over n plus 1. This is just fun. It's not really like, there's nothing deep happening. I'm just showing you something cool. Look, 1 over n plus 1. Ah, look, this thing now is 1 over n factorial, yes? Plus, sorry, no. In fact, I want to pull out a whole 1 over n plus 1 factorial. Sorry.